All right, and yeah, so we'll go right into section 40 for, I don't even know what the title is, but basically it's going to be about big data, PySpark, MapReduce, and stuff like that. So I'm going to show you guys a little bit of those things. Note that I'm not going to really show too much PySpark, what's it called, coded by itself. I think I'm going to talk more about distributed computing and big data as a general kind of like topic. So I will show a little bit of MapReduce. We should have enough time. We might have enough time to get through an example and stuff like that. But I want to emphasize is that like, I just want to show you guys more of the concepts of stuff like this, how to approach these kind of concepts. Okay. So let me go and start sharing my screen. Share. Okay, cool. And all right. So the big thing about the reason why we're going to talk about like MapReduce and PySpark and stuff like that is something called big data. And it's kind of like a cliche now. We talk about big data. It's like, oh, like what is big data? So it's kind of actually an important point is that big data has a few definitions and it's not super agreed upon. But the way you can think of big data is like why we have to think about data as something being different with big data. It's basically like a different amount makes it a different kind of thing. Is that by having essentially, we'll talk about in like quantity of data, but if you have like a large amount of data, you have to approach it very differently than if you had it all be able to fit on your computer. If you have terabytes on terabytes of data, you really can't do the same processes we've been doing for the past, few months. You kind of have to approach it in a very different way. And note that there's no clear definition of what we say is big data. We have some like general kind of like, guiding principles of like when something is big data, but you can also have things like small data and like medium data. And sometimes medium data like looks like something like, oh, we have to approach it as if you're big data. And then you realize, oh, we can actually approach it just like we've been doing everything else, like relatively small data sets. So there's no firm line of when something becomes big data by itself. But a big part of this is going to be the fact that you just can't fit it on one local machine. Basically, you can't run this on your laptop. You can't run it on a desktop. You might not even be able to run it on like a really souped up desktop, like a professional grade, $20,000 computer by itself. You might have to actually distribute it. Basically, just that's the only feasible way to do it. And that's really where big data is coming in. Okay. So this is actually like a real term called numbers everyone should know. And this is actually, I don't think it's talked about in the curriculum. So anyone who's gone through it right now, I don't think this is directly stated, but there's this thing in big data and actually just computing in general. It's called the numbers everyone should know. I think it was originally from this original blog right here from Jeff Dean and Peter Norvig. I have the little blog right here to talk about this. And these numbers will change and stuff like this, but I think it's important to understand what's going on here. So if you don't know how a computer works, we're going to do some really basic stuff about how computers work. So there's basically four main parts of a computer that we really care about. Obviously, there's more details on this, but the basics. The CPU, which is basically the brain, is kind of like essentially the fastest part of the computer. This is the thing that's basically doing all the computation, doing all the thinking for you. This is like on the orders of like, half a nanosecond, kind of like per operation. And note that like, depending on the CPU kind of deal, it might be faster or slower, but it's on that same order. CPU tends to be the fastest thing, and we really think of it like the brain. This brings us into like memory when we talk about like RAM. So I think most people know what RAM is and stuff like, or at least have heard the word RAM and everything like that. And you can think of it as like short-term memory. This is actually very fast, relatively fast compared to other parts. The only thing faster than this is really the CPU. And we call it short-term memory essentially because you can't store things in RAM like over long periods of time. And by long periods of time, I mean basically when you turn on and off the computer. It's called random access memory. Essentially, not really super important, but basically the idea there is that it can get access to the memory wherever it lives. So it basically can do that very, very quickly. And the main thing for this memory is going to be for data science is basically it's going to be feeding instructions or data to the CPU to do all the work. And then once the CPU is done with it, the RAM is going to move that data, move that information off to something else, like either the next process or, store it onto the disk. So like saving the data there or, printing it out or doing something with it. Okay. And then storage, I think most people kind of have an idea of this. This is like a SSD or a hard drive, an HDD, right? This is long-term memory. If you ever remember, I think most computers now have SSDs, but if you use like a hard drive, like a physical hard drive, they're pretty slow. It's not ideal and stuff like this. It basically takes a lot of time for anything to be written from RAM onto a storage, like an SSD. It takes the most amount of time, at least on the actual local computer. So this is something that we want to like really think about. It's like, okay, if we have to constantly read or store things on this, take a long time. However, we can store a whole lot more. It just tends to be really cheap. So it tends to be have a lot more space in RAM. RAM, I think most like really high-end data science computers at the highest I really tend to see is 128 gigabytes of RAM, where obviously storage can go a lot higher. Terabytes pretty common nowadays these days. Okay. And then the real slowest part is the network. And essentially this just means it's connecting to other machines, right? So this basically is going to take the longest amount of time, basically. And this network can also be like locally on the computer. So if there's multiple computers connected on the same like, you know, local network, it's still going to take the longest amount of time essentially versus the CPU to the RAM or the RAM to storage. Okay. So I will put this little link right here, which kind of lets you kind of play around with like the different years, which is a really great thing that someone put together, is you can kind of adjust it and see what year and stuff like this and how long each part takes and stuff like this. So it's kind of a fun thing to play around with and stuff like this. But this kind of gives a good example of like when things are a good big data set. And because it comes into this concept, something called thrashing. And so does anyone know what thrashing is by chance when we talk about computers? Okay, so yeah, thrashing ends up being basically, I kind of explain it as like your CPU is super bored, twiddling its thumbs, waiting for things to happen. And basically it's waiting for all these slowpokes, like you can think like the storage and the memory. So if I draw like a little diagram, this is kind of like how I envision it in my head, is that if you have something like, you know, long-term storage, so let's say like your SSD, and then you have like this RAM. I'm trying to make it like distinguishable. And then we have our CPU. So what's going to happen is that we have data on this like hard drive, right? And essentially when I take this data, the RAM will say, okay, let me go to grab this data here. And it's going to bring it over to the CPU. But it takes some time for it to basically bring it over to it. So you get it over to it and you feed it to the CPU, and the CPU is like super fast, like, okay, cool, like crunches it away and says, okay, RAM, take it away. And then RAM has to basically like imagine doing this like kind of slow arm, kind of moving it forward, takes it whole thing and then moves it back over into long-term storage, kind of moving forward. So the thing is that if it takes this long time for RAM to kind of like give all the instructions to the CPU, and the CPU computes it really quickly, and then it has to bring all this data back or this information back to long-term, get some new stuff, bring it back to the CPU. A lot of times where most of the work is being done, the CPU is doing nothing. Essentially, it's just waiting there. So if you ever get through like, you know, on a Mac, I think it's Activity Monitor, or if you go to like on Windows, a Task Manager, something that can see like what's going on in your computer. What thrashing happens is when basically your RAM's full, your RAM's doing as fast as it can, it's doing as much as it can, but your CPU is just sitting there. So what you'll tend to see is if you imagine like your CPU usage will look something like, you know, like 1%, like this, but then like your RAM, and this is like usually like, you'll notice it's like your RAM, like, you know, things get really slow, things get jittery, things don't open very quickly. Your RAM is like completely like almost 100%, if not 100% completely full. And essentially it means like, hey, the CPU is doing nothing while the RAM is trying to do all this work. And essentially this is a big bottleneck. So our big thing is to avoid thrashing. Essentially is to allow us to keep feeding the beast of the CPU to do all the computation for us. And so that's when big data really comes in. It's like, okay, like, well, if your computer can't handle with this much amount of RAM, we can increase the RAM, or we can split up the job where essentially we have different parts of memory essentially feeding different CPUs or the same CPU. So that way the CPU can keep working along and everything like that. We want to keep CPU nice and busy, like a factory assembly line. Okay. Does that make sense of this like concept of thrashing? Okay, and this is pretty common where like if you see thrashing, it means that you have to kind of reassess of like what you need to do with your kind of computation setup. Okay. All right, so moving right along to the 3 V's of data, and one of them is not Victor. Sorry to say, but the main thing, the three V's of data, basically, should I say of big data, but essentially the ideas of volume, which is like large amounts of data, velocity, quickly generated, or variety, so unstructured. And so we really say like data is big when it's one of these three things. And basically when you have a large amount of data, well, if it's one of these three things, it means that it might be better to actually split up the work amongst many different parts, many different computers or many different workers essentially, and work on those together. And you can kind of think of that like there's a trade-off here, right? Is that this network is super slow. So it's going to take some time to like actually transfer this information to get this work done. But if if a group of computers can work on many the same problem, but like in different parts of it at the same time, that might be faster than having to try to get like one computer to do all the massive work and stuff like this. And you can think of this like volume. Like if you have a large amount of data, if you have like 500 gigabytes of data, well, that's not going to fit on your RAM. Your RAM's never going to be able to pass it all to the CPU all at once, right? Essentially, it's going to have to chunk it up and do some kind of crazy stuff with it. It might make more sense to split up that data set into smaller pieces and pass it on to different computers where it can fit in their memory and do that part. Velocity, where this data might be coming in like in real time, coming through. If there's a huge amount of data coming in at a very fast speed, well, the thing is that computer might not be able to handle like that RAM, feed that beast, the CPU. It might be working on trying to feed it in all the time, and it's not being able to catch up. So maybe it makes more sense to split it up amongst multiple computers where maybe the data sometimes comes to computer A, and sometimes the data comes to computer B, and then calculate it together, and then basically organize it all together at the very end. And then variety is kind of an interesting one. Variety basically comes down to the fact that there might be some other pre-processing going through. So the terms in here, in this case, if we knew like a little more data engineering, there are things called like data warehouses, which you can kind of think of like SQL or data frames kind of thing. There are also things that are much more popular now called data lakes, where essentially you have a variety of different data that's just basically thrown in the lake essentially. And essentially you have to take out that information, do something with it, and then pass it on to do like your next steps. And if it's a lot of variety and stuff like that, it's hard for the computer essentially to like, it does best when it's expecting the same thing. So it might make sense to say, okay, this computer is going to handle this kind of data, this computer is going to work on this kind of data, and that way they kind of split up the job a little bit better. You can kind of think of it like as people, it's like if you had like, okay, your specialty is like if you're building a car, your specialty is like dealing with the tires, and your specialty is dealing with like the engine. Like that's essentially what's going on with the high variety. Okay. So the main idea here is that big data really is talking about when you can't put it on one computer. And usually it comes from the fact that it's one of these three attributes of the data, whether it's the high volume, high velocity, or high variety. Okay. Any questions on this concept? Looking pretty good? No? Yeah. Okay. So I have no questions, so I think I can move on, right? All right, so I only have 5 minutes, but we'll get right through it. Okay, so this is where I'll probably get to this part right here, and then we'll maybe call it. So the next big part of saying, okay, like we agree, say, all right, we have big data, what do we do? So one thing we can do is basically doing parallelization in distributed computation. So this is actually kind of similar to what the curriculum kind of shows a little bit, but distributed basically means that we split up the task and it's executed by different workers. And one thing I should make clear, I keep saying like, you know, different computers, and sometimes I say different workers. It can actually be that multiple workers are on the same computer. Essentially, this is something like CPU threads and stuff like that, if you're familiar with threads or cores in a computer. Essentially, they're like little tiny brains. And so sometimes, for example, if you have an 8-core computer, you might be able to have 8 workers. In fact, some CPUs, and actually most CPUs now, actually have something called threads, and each of those workers might have 2 threads in addition. So you might have 8 cores, but 16 threads, which means you can do 16 workers and do things all at the same time. So just kind of know I use that terminology back and forth. But the main thing with distributed is that multiple CPUs have their own memory, and that multiple CPUs share via a network. So here's a kind of 2 different ways you can think of distributed systems. One is basically you can all talk to one server, and the server is basically kind of like passing back and forth the information, and it's aggregated to here, so the computer doesn't have to know anything. There's also peer-to-peer networks where essentially each computer can pass directly to the other computer. Doesn't have to be managed by something. And these are both distributed networks. Again, the main idea here is that you can't put it all on one computer. So we have to have either some kind of management system where it talks to each computer each does a little bit of work and go from there, or the computers manage themselves in some kind of like agreed upon structure. So you can think of things like Bitcoin would be something along with like peer-to-peer network, where essentially there's a protocol to say, this is how we talk with each other essentially to do this computation. Okay. So that is distributed. Going a little bit to sequential is what we classically have been doing with our computer. Essentially, is like we start off with a problem, and then we have a bunch of steps, and then step one, like a bunch of step 1, step 2, step 3, step 4, and then it goes on to the CPU, like the full CPU, like one computer. And essentially means we take one step at a time. You can't do step 3 before you do step 1. So essentially means you have to do it in sequence. And this is usually what we go through. And note that distributed computing can still have sequential computing too. Is that essentially each computer can do a sequential thing, and maybe it's just waiting for the next computer to do the next part. So distributed doesn't necessarily mean parallel, which we'll talk about next. Okay. Does that make sense to everyone? What sequential means? Okay. So parallel is probably the strangest one, because usually I don't think we think in parallel, but parallel basically lies on the fact that we're executing tasks in a non-sequential order. So the idea here is you have multiple workers or multiple computers, we'll say like CPUs, right? And note that it says share the same memory. This is technically like an older idea. It doesn't technically have to share the same memory to communicate. You can have distributed like this parallel computing. Usually that's kind of like a little different, especially now that networks are much faster. But the main idea here is that we have multiple CPUs working independently from each other and then aggregating it usually towards the end of their process. So here you can think of like the problem split up into multiple spots, and then each CPU, which is each like row here, each worker is doing its own work independent to the other one. So they might not all finish at the same time, but the idea is that they would each work on their task and then collect their information all together. And that's how you would complete this task. So the main idea here between parallel and distributed is that parallel basically means that you're computing these things independent from each other. And distributed has some kind of like, you're working on different tasks, but they could potentially be related with each other. So sometimes it's hard to kind of distinguish what's distributed versus parallel. Usually they're one and the same, at least now in modern days and stuff like this, but it doesn't necessarily have to be. This can also be done all on one computer by itself, and just have different threads or different workers, versus this one has to essentially use some kind of network where they're distributing out the work and then going from there. Okay. All right. Any questions on sequential, distributed, or parallel? Pretty good. Okay. So yeah, I realize I'm kind of low on time, but I think I have enough time to just talk about a little bit of tools of the trade. And then maybe next time we'll talk a little bit about MapReduce, and I'll show you guys some MapReduce code, what that concept looks like. Okay, so some tools that we can use, right? So this is where basically, like, I will tell you, like, there's a huge amount of tools. This is definitely not all of them. In fact, there's a whole bunch of here that like it's kind of weird. Like if you start looking at like all the different tools you can use for like big data and stuff like this, it starts sounding like Dr. Seuss. Like there's Pig and like Hive, and there's Hadoop, and there's all these like sound like really kind of strange sounding words. So just know there's a huge amount of different things you can do. And there's actually a little joke. I should have found that picture, but there's a little joke that says, you know, from someone's like a data scientist resume, and it says to a recruiter, it says, recruiter, some of these things are data science tools, other of them are Pokemon. Tell me which ones are which, because it's kind of ridiculous how many weird different words. But the main one that we're going to kind of talk a lot about is Hadoop and Apache Spark. So Hadoop, which is like this little elephant guy, there's a whole story about this thing, but I won't get into details right now. But just know that Hadoop is based on Java, like Java programming, not JavaScript. And it's kind of considered old school. It's technically slower since it has to write to the disk each time. Remember, the disk is like the hard drive, which is like the slowest part. So it tends to be a little bit slower. Its storage basically uses something called the Hadoop file system, or HDFS. Data processing is through MapReduce. So MapReduce, super confusing, but MapReduce is actually a concept of programming, but it's also a programming language, which can be super kind of confusing, but just know that's it's processing and also does some resource management. So basically it's there's some director that tells it how to deal with all the different parts of how we distribute out the work and stuff like this. And so now the new kid on the block, which is getting very, very popular, is Apache Spark. So this is when we talk about like PySpark and stuff like this. So Apache Spark, again, is also written in Java. But what's kind of cool is Apache Spark holds the data in memory, so like in RAM, which whenever possible, which means it's much faster, or it can be a lot faster. What's also nice too is that Apache Spark will be built on top of Hadoop, but also on like S3 on the AWS. So AWS, Amazon Web Services, think cloud. S3 is a very popular method of storage and data storage and stuff like this. And so what's kind of nice is that Apache Spark can also be built on not just on the newer stuff like S3, but also kind of on these older systems like Hadoop. To kind of put in perspective, most places starting up will probably use Spark first, but there's still a lot of like modern industries that use Hadoop. For example, I believe Facebook uses the Hadoop HDFS system. And the reason why they just don't have they basically said, it's technically slower, but it's worked well enough for them. So just know that basically either one of these can be good. But Spark has really been like kind of like the king of data science right now because it's really good at something called ETL. So extract, transform, load. And it's also really great at machine learning in distributed systems. So it's designed to do that kind of stuff, which you guys have learned about some machine learning stuff. Okay, but just know it's not always the best tool. So sometimes you can use these tools, Hadoop or Apache Spark, depending who you're talking to. But what is nice about stuff that you can do with Spark is that you can use it in local mode. So you basically don't have to design a whole new cluster just to test this out. You can do it all on your computer, which makes it nice and easy. Okay. So that is kind of like overall big data. I know I didn't really show you guys any code today and all that stuff, but I think hopefully this kind of gives you an idea of like these tools. And I will tell you, there is so much more. Like I should find like a good like the whole diagram, all the different tools you can use for like, big data and stuff like this, because it is massive and I don't know everything, which hopefully that makes you feel a little better too, is that no one knows all of these things and you use whatever you're using in that industry and stuff like that. Okay. I know I'm kind of over time, but do you guys have any questions or anything you guys would like to ask before we head out? No. Okay. Cool. And I'll save this. These are already up on the GitHub repo, but I'll save MapReduce and kind of talk about like what MapReduce looks like and how this kind of interacts and stuff like this, how it flows with distributed and parallel systems, and then actually showing you a little bit of code of like, how you can run some of this stuff. And actually one thing I like to do is like, I don't like to use PySpark on this. I like to show like the concept of like what MapReduce is doing versus like just trying to implement it in PySpark. But we'll save that for the first few minutes of next time. Okay. Cool. All right, I'll stop recording here.